All right, guys. Hope everyone's doing well out there. Hope everyone's having fun quarantining, I guess. But anyway, so we're going to continue on with chapter 14. I know we started doing chapter 14, section 2 last video. We're going to finish it today, go into a little bit of part 3, and then we'll call it a day. So, um, we talked about when the sun was created or made or formed, and then we talked about when Earth started to form. So, sun was like 5 billion years ago, around. Some people say 4.5. And then Earth was about 4 billion years ago. So after this, we started to want to learn, okay, where did life come from? Where did life start? And how did we start to get all these macromolecules that made up life? So to start off, these two guys, Oparin and Haldane, they had a hypothesis that we had some gases on early Earth. And these gases were ammonia, which I have in parentheses there as NH3. Okay, so nitrogen bonded to three hydrogens. It was hydrogen gas. It was some water vapor. So it wasn't water, it was the gaseous form of water. And then carbon. And carbon was found in methane, which is carbon bonded to four hydrogens. If you guys want to know what methane is, if you've ever seen someone like go behind a cow and try to light a cow fart on fire, a cow fart lights on fire because of the methane in cow farts. But anyway, so their hypothesis was that with these original gases, if these were the ones that were in existence on early Earth, at really, really high temperatures, these gases could be transformed, and in the transformation, they could become some of our macromolecules. In this one, they say it could become amino acids, so that's part of our protein macromolecule. The second part was that as Earth cooled, the water vapor, which again, gaseous form of water, started to cool and it became all of our lakes and all of our oceans. Okay. Um, they also thought that different compounds would collect in the water. So all these other gases would collect in there and they would form proteins, lipids, all of our macromolecules. Okay. Again, guys, I know I'm talking faster than you could probably write if you're doing your notes or if you want your notes. But all this stuff is on Google Classroom or my website. You can go on either or to get the PowerPoint. So they developed these two very nice hypotheses, Oparin and Haldane did. But the problem is they didn't test it. All right. To me, that's a problem. That's like, going back in history and being like, okay, you got a bunch of old dead guys now, but they were like, oh, okay, well, the Earth is clearly flat. Well, okay, let's do a hypothesis. Well, if you walk to the edge of the Earth, you could fall off. Okay, how many people have fallen off the Earth? Well, if they've fallen off the Earth, they're dead, so we don't know. Okay, there was no way to test this hypothesis. Okay, now we for sure know, based on different eclipses, that the Earth is definitely round. We could test this hypothesis, but just saying the Earth is flat, okay, yeah, that's your hypothesis. You've got to be able to test it. So Oparin and Haldane, they didn't test the hypothesis of the early gases that they assumed were on Earth. And then came Miller and Urey. So some time passed. Miller and Urey decided, okay, we can do this. We can get an experiment ready. And they did. They got an experiment to be able to test to see if they were right with their hypotheses. If it was ammonia, if it was water vapor, methane, hydrogen gas, all on early Earth. So what they did was they got a chamber and they put all these original gases in this chamber, okay? And their hypothesis was that it wasn't just, like the water settling in the vapor and turning into lakes that formed all these amino acids and nucleic acids and everything like that. They think that we needed some energy source to transform these gases. So we needed some kind of energy, not like ATP, like actual energy, in order to get these gases to transform into our macromolecules. So what they did was they actually put electric sparks in with these gases. All right. So here's their whole chamber here, guys. You don't have to worry about this too much, but they put all the gases in, they put electrical sparks in, and then they found that in the end, yeah, we got amino acids out of it, which is really cool. So that's what they did. Problem is with this, guys, is okay, they were like, all right, if we put electricity in, cool. we can get amino acids. All right, in early Earth, where are we going to get electricity from? And then they realized, oh, a bolt of lightning. Okay, so they realized that the bolt of lightning came down and transformed these gases, and that's how we got our early macromolecules, our proteins, our lipids, our nucleic acids, and our carbohydrates. All right. Um, so after this, a kind of contrasting hypothesis to Opar and Haldane, Miller, and Urey's whole bit was that, okay, well, maybe these macromolecules didn't come from all these gases and a bolt of lightning changing them. Maybe they came from something else. Well, in 1970, late in 1969 to be exact, we had this meteor fall into Earth's atmosphere and it hit in Australia. Um, so they studied this meteorite, and here was our meteor. Okay, that's the original one. Um, and that came down, like I said, in 1969, fell into Australia. And when they were studying it, they found that there was actually amino acids on it. And if it came from outer space and these amino acids were on it, we know that those amino acids formed in outer space. All right. No, it doesn't mean there's the existence of aliens out there. Or maybe it does. Nobody knows, right? But what that means is that some of these macromolecules could have actually formed in outer space, came to Earth, and then somehow gave rise to the first life, right? Now, with this meteorite, like I said, it was, it fell in Australia. Yeah, these kind of cute little creatures there. That's Australia, right? But no, back to this. So it fell into Australia in 1969. But the funny thing is they're actually still studying the same exact meteorite today. In January of this year, 2020, they did further research on this meteorite because, over time, guys, I mean, let's think about it. It landed in, well, let's just say 1970, all right? 50 years have passed. All the technology has gotten a lot better now, so they're doing further studies on it. And going to half-lives, what we talked about last video, the half-lives start to, or we start to get better technology to test our half-lives. They found that there was silicon on this meteor that dates back to 7 billion, with a B, 7 billion years ago. That's crazy, right? Okay, let's talk about last video. We talked about the sun. It was like 4.5 billion to 5 billion years ago. It was formed. Okay, that's our hypothesis. But this meteor actually has silicon on it that's older than the sun. That's fantastic, right? That's incredible. So things we're still learning to this day. Now, when we have our macromolecules, sure, we got our proteins, we got our lipids, we got our nucleic acids, we got our carbohydrates. Okay, we can say that they formed. Either they came in from different meteorites, or they formed from the bolt of lightning with all of our gases already existed. Either way, it could have happened that way, but that doesn't tell us how these macromolecules then gave rise into living things. Let's recall, the smallest living thing is a cell, okay? That's the smallest thing that is actually categorized as being living. Macromolecules are not. So where's the connection between our macromolecules and our cells, okay? So Sidney Fox, there was a bunch of more studies done after this, okay? So there was these microspheres and coacervates, fun words, right? These were pretty much a bunch of macromolecules that bonded together. Now they weren't living, but they think these were like the earliest parts of cells, okay? So they found it in a lab that microspheres are going to form spontaneously, all right? And they are going to be made from organic chemicals, from our macromolecules, right? The microspheres, they were kind of just like, we can call them empty vessels almost. It's like a spaceship without anything inside. So we think that they formed our cell membranes, okay? It was proteins, probably some lipids in there too, making spherical shapes. And the coacervates look like little water droplets, but they were just droplets, and they were a bunch of different macromolecules just in these little droplets. So we're starting to have the macromolecules come together. All right, the microspheres is going to be our cell membrane. The coacervates is probably going to be everything inside of our cell membrane. All right, so we're still not to life yet, but our macromolecules are starting to work together. All right, we also looked at the reproduction of these two, the coacervates and the microspheres. We saw that they can grow and bud, which looked really, really, really similar to bacteria reproducing by binary fission. Okay. Problem was, the main thing for us guys that makes us living is our DNA. Okay, that tells us everything about us. That gives us all our characteristics. The microspheres, the coacervates, no DNA. All right, so they can't evolve. They can't respond to stimuli, nothing like that. And that's the end of our pretty much first life forms that were, I guess, not living. Now we're going to get into the living part just a little bit today. All right. So let's talk about DNA. We talked about DNA a few chapters ago, and you guys know that DNA has a double helix. All right, it's double stranded. So we got one strand of DNA connected to another strand of DNA. All right. And we learned that it gets transcribed into RNA and translated into a protein. Okay, done with that. That's old chapters, right? So recently we've wondered, okay, well, why do we need this RNA? Okay, why can't we go, instead of going DNA to RNA to a protein, why can't we just like eliminate the middleman, eliminate the RNA, and we can go from DNA right to a protein? Well, here you go. Okay, they found that as a protein is formed, we are going to have a long string. And after this long string of proteins formed, it folds into one another, okay? And they thought that it really, really looks a lot like the formation of DNA because we have hydrogen bonds in between our DNA connecting our two strands together, okay? So here is your protein, and you guys can see that it's all connected together. And as it folds, we start to get kind of where the S's are there on the second picture. Those are hydrogen bonds in between our two amino acids. Let's skip this one, guys. But anyway, going back to the DNA and the proteins just for a second. Okay, as we have this DNA, all right, and as it is hydrogen bonded together, all right, so we got our two strands hydrogen bonded together. They're thinking that since it was like kind of a part of evolution, since the hydrogen bonds brought everything together, they're thinking that same evolutionary process happened in order to bring our protein to fold. Okay, but in the 1980s, we had a guy named Thomas Setch, and he found that there was RNA that was unicellular and it acted like enzymes. So it acted like a protein. If you guys remember, proteins are enzymes. All right. He called this a ribozyme. All right. So it's RNA that acts like a protein that acts like an enzyme. All right. And that's pretty much all you need to know, guys. It's just an enzyme like RNA. Okay. So if we go back to our DNA, okay, why do we need to go to RNA to get to the protein? Well, if you remember from DNA replication, we always have to start with an RNA primer. All right. In order for new DNA to be formed, so we can like reproduce our cells, so our cells can keep growing and then making more new cells, we need to have this RNA, little part of it, in order for this to happen. Okay, without the RNA, you don't get any new cells. Without new cells, your body doesn't grow. Without growth, you die. Okay, but the RNA primer was needed. So this tells us that originally we think RNA was here first, and then DNA actually evolved from RNA. So the RNA was here first, and then DNA came. And this tells us why we can't get rid of, if we're going to do a protein, DNA goes to the RNA, which goes to the protein. This tells us why we can't get rid of that middleman. This tells us why we can't get rid of that RNA, because it was here first, and without the RNA, we would never have DNA. Okay. Here's another hypothesis, guys. Granted that, okay, we just went over RNA was here first, right? So we got these microspheres, we got this coacervates, The microspheres were our cell membranes, okay? So think of this, picture a world, all right? It's all like barren and desolate, and there's nothing around. We got all these microspheres just chilling there, and they're kind of just, you know, just on the land, I guess you could say. And we got all these RNA nucleotides just around. It was almost like they were trying to collect Pokemon, all right? So the microspheres were like, okay, I'm going to get this RNA, and they start pulling nucleotides in. And after some time, they got enough RNA to actually form a whole molecule of RNA. And then when they had this whole molecule of RNA, they became living. All right. So that's another one, another hypothesis. I don't really care for that one that much, but that's just one theory. All right. So later on, Setch found these ribozymes, okay, which are the catalysts of RNA catalysts or RNA enzymes. So they can actually reproduce their own RNA, right? And that was again still before DNA. So this started to lead to, okay, well, these ribozymes can catalyze reproduction of our RNA whenever the RNA is in our microspheres. And I think we're going to stop here today, guys. Have a good rest of your day.